Hi everyone, I'm Jack. The point of this somewhat busy looking slide is that if you are thinking about phenomena that are not at all relativistic, slow moving, flat space-time, nothing particularly exotic, the usual assumption is that everything that you see will be described accurately by the Schrodinger equation. And so if you do an experiment and find that your data is consistent with the Schrodinger equation, this is a very boring result. It's not, you haven't learned anything. Unless maybe there's some sense in which the experiment that you're doing is seeing quantum mechanical effects in a regime that hasn't exhibited quantum mechanical effects before. And so the question that we're very interested in is, to what extent does the Schrodinger equation, the usual one up there, accurately describe large objects? And I will start by saying there's no unique definition of largeness or macroscopicity. There's also no unique way in which phenomena that you observe might differ from prediction. There's an infinite number of ways to be different. Nevertheless, there are some somewhat broad notions of what small corrections to the expected dynamics might look like. For example, you could take the usual Schrodinger equation and just ask if whatever exotic new physics you have might be parameterized by nonlinear terms where the nonlinearity is higher powers of the Schrodinger operator. Turns out that this is you could be completely model agnostic and just say, hey, it's a reasonably well-behaved mathematical correction. We can go look for it. It can also be derived, this is my understanding, from proper quantum field theory by combining local Lorentz invariance and Planck scale discreteness. Basically, it's a term whose mathematical form means that you'll see the largest effects if you have an object with large mass, and if that object is undergoing large motion, because it's under that case that your wave function has big derivatives with respect to space and time, and so these higher order terms would be large. So to study that, we have a way of confining a nanogram of material, in this case superfluid helium. Nanogram is not a lot. But we can actually detect its individual quanta. We can detect the individual phonons of vibrations in this object. And this is the kind of data that we take by driving a harmonic motion of that nanogram of liquid helium. We can take a lot of very quantitative data on these individual phonon effects and basically fit it to the usual quantum mechanics, Schrodinger's equation, textbook stuff, plus a correction that is this higher power of the Schrodinger operator, taking this factor here as a fit parameter. Normally, we would expect this to be 0. So we just take all this data in a relatively large object that's being driven to very large amount of motion, basically 20,000 phonons worth of excitation. And when we take all this data and fit it, this is the extracted, this is the value of this nonlinearity parameter, here converted to sort of natural units of the length scale. This is just lots of different data, but the global fit is shown as the red line here. And so we find that it's at least consistent with 0. And depending on how you interpret this data, you could attribute this to length scale for this nonlinearity that's sort of on the scale of 10 to the minus 19 meters. And that's a length scale that's set by the 0-point motion of a nanogram-sized object, which is about a femtometer, and our ability to drive it into really large amplitude motion, which makes you more sensitive to any nonlinearities. So that's most of what I was going to say. This is work that was all done in Wright Lab. This is sort of done by accident. We were just curious about what would happen if we took this thing and drove it to large amplitude motion, and in sort of fitting the data and understanding whether there was anything interesting in it, sort of bumped into this theory and to this analysis the way. So we're thinking a lot about ways to push this a little bit further.
Can you say a few words about what would be the next step?
Yeah, so we have a couple ways of just scaling this up physically. Right now, that's an acoustic optical cavity that's formed between the end faces of 2 telecom fibers. And for other applications, that's a really nice way to build devices and cavities. But if what you're interested in is just getting more mass oscillating in there, we think we know ways of scaling this up by some orders of magnitude.
Very well. So, is there a prediction from these Planck scale discreteness models of where will the length scale affect
No.
the next one?
So this is like way above my pay grade, but when I read the papers, what they say is, if this is Planck scale physics, okay, so first of all, two approaches. The one I prefer is just to be completely model agnostic. It's just a possible term. We fit for the coefficient. In that story, they claim that even though the sort of corrections to the non-relativistic limit come out of thinking about stuff at Planck scale, they claim that the scale of this nonlinearity doesn't have to be 10 to the minus 34 meters. I don't know what their reasoning is. If anyone else does, please feel free to explain it to me.